Okay, so I kind of skip back a little bit. So I kind of go over the kind of the review of session 2.1. So this is how we're going to run these weekly review sessions. So I'm just going to briefly go through the materials because I assume that you guys already watched the lectures. Honestly, I'm the tutor, so I'm not like a lecturer, so I wouldn't want to like repeat the lectures again. So we're just gonna go through like the main points and what you should know by this time, and if you don't understand some of those points, then you should look back at the lectures and before proceeding to do all of the problems that you have. And then I'm just gonna go through some of the example problems of these sessions. And like today, we have 4 sessions, 2.1, 2.2, 2.3, and 2.4. So I'm just gonna go through like a few examples for each of them. Most of them is like the most representative problems that you should know. So if you're struggling with any of them, that means that you're not like fully understand the lectures and you should actually work on it more. But if you understand on it, kind of like you get around 70% or 80% of the exam with all of my practice problems. The extra 20% is going to come a lot from your practice, how much and how many problems you actually solve and understand from the suggested problem on Canvas. So the first one is question 59 of sessions 2.1. So determine if f prime 0 exists if fx is given as a piecewise functions like this. So as we saw earlier in the previous slide, we have f prime 0 is defined as limit. There are 2 definitions of the derivative at a point. So one of the way that you can do it is this way, 1 over x minus f of 0, which is and then x minus 0. So there are 2 definitions that you can use. I mean, we can solve this one using both, but it's essentially going to give you the same answer. I'm just usually stick to the one I usually do, but in some other cases, the one with limit of h approaching 0 is going to be a better option. So here, f of 0, when you plug in, is you don't need to plug in. It's giving you as a piecewise function, so it's going to be 0. So now the derivative is going to be the limit of x sine 1 over x divided by x. And this one is going to be limit of x approaching 0 sine 1 over x. Now let me think about it. When x approaching 0, where do 1 over x approach? It's going to be 1 over a very small number. So it's going to infinity. And sine of infinity is something that doesn't exist. Because now you think about it, the function of sine when you draw it, so it's going to be fluctuating between -1 and 1. Sorry for that. It's technical. It's a technical thing. So it's going to keep fluctuating from -1 to 1, regardless of like what value of the angle. So when the angle becomes super very big, or like either it's positive infinity or negative infinity, the value is going to keep fluctuating. It doesn't stop at a single point. Therefore, we said that the limit doesn't exist because it doesn't actually approach any specific number. Therefore, you conclude that this derivative at that point doesn't exist. Now, when we're going to go to the second example. If you have any questions at any time, as I said, feel free to type it in the chat room. It's gonna pop up so that I can see, and I'll stop at any time to answer your questions and maybe like explain further if you want to. And we'll go to the second example. Is question 60. So this is kind of like a side note. There are 2 ways that you can do the suggested problem and like increase your practice. So what happened in the book is that all of the art problem, usually they have their answers in the book and they tend to be slightly easier. So after you've challenged yourself through the suggested problems and you feel like, okay, I'm good at it, but if you want to check more, you can try the even number problems, because those are usually harder and they don't have the answer in the book, so you cannot like look it up, so it's gonna be a little bit more challenging to solve them. But if you actually understand it and just want to like test yourself, that's a better options to try. Then we have example 2. So determine if dash 1 exists if you're given a different function. So now instead of x, you have x squared. So I'm just gonna do kind of like the same thing. Limit of x approaching 0, x squared sine 1 over x minus 0 over x minus 0. So this one is going to give us x sine 1 over x. So it's going to give us this. Now, I wonder if any of you have seen one of the expression. Give me a second. It's kind of, I should have done like kind of a math, like check out your background, because I don't want to bore you guys out with the very basic stuff, but at the same time I don't want you guys to like lose track of what I'm talking about. So here we have that. I didn't do the sessions for last week because that's usually how we work, but can you guys please answer me if Dr. Katarzyna went over something like the squeeze theorem? Have you guys ever heard of it? The squeeze theorem. Okay, if not, so I'm just gonna introduce it this way then. Okay, sure. So that one's gonna be helpful. Okay, so in this case, okay, sure. So in this case, we can use the squeeze theorem to figure out this limit to see if it exists or it doesn't exist. So the way that we do it is say, we always know that sine, as I said in the previous example, is always going to be squeezed between -1 and 1. And it's the same for cosine as well. So if you have like another problems that you encounter and you see it's cosine, you can try to use squeeze theorem because it's always going to be bounded between -1 and 1 as well, regardless of what the angle is. So when you multiply x, and here x approaching 0, it's going to be x sine 1 over x divided by x. Someone might argue the fact that you don't know if x is positive or negative, and then these two signs might change signs, right? But I mean, essentially, if it's a negative, what you end up having is this going to be like this way. And then when you use the squeeze theorem, like what I'm going to do now, it's just going to give you the same answer. So we have as limit of x approaching 0 of -x is equal to limit of x approaching 0 of x. And so this one, both of them are going to be equal to 0 because x is going to approach 0 right now. And so by the squeeze theorem, we're going to have the function in between that is squeezed by the two boundary functions outside. And when the two boundaries function approach the same number, then you have the middle function is going to approach the same number as well. So therefore, we have this one equal to 0. Now, a lot of time, my student usually ask me, how do you know that you're going to use the squeeze theorem here? Again, when you look at this one, if you plug in x equals 0, what you have is 0 multiply a number that does not exist. So there's not actually a way that you can just plug in the number and figure out what this limit is. And so when I look at the function further, when I usually have sine and cosine, I usually use the squeeze theorem because squeeze theorem give you a sense of the trigonometric function with sine and cosine because the fact that they always squeeze between -1 and 1. So it makes life so much easier. And I mean, it's just come from a lot of practice. And that's also like my slogan when I try to tutor people. A lot of my students just go through a few sessions and they don't go anymore because I make them do a lot of practice and they learn like how to do safe learning and they don't actually need like much help unless they actually like need help with like understanding the concept. But after that, trying the problem is more important, and actually understand the problem as well. So that's what we have for example 2. Now it's example 3. So I've seen this one in Dr. Cash's previous quiz questions in the previous semester. So I think it's a very good one to try out. So we have the function fx and gx are pictured as that. Let hx equal to fx minus gx. Calculate h prime 4. So it's kind of like a strange one, but I think it's a very interesting one to try, because if you actually understand the concept, this one is actually pretty easy. So we're trying to calculate h4, and we're doing definition of a function, definition of derivative of a function at a point. So here that point is 4. So we have h prime of 4 is equal. Now if we use a limit and we need to use h x, so what I'm doing is x approaching 4, hx minus h4 divided by x minus 4. Now they give us hx is fx minus gx. So what I'm gonna do is, that's like the only options that I have so far to figure out what hx is. So I'm just gonna plug that one is, you have fx minus gx. And for h4, you translate it into f4 minus g4. And then you put x minus 4. Now what you end up having is that you have fx minus, you take this f4 out. I try to group everything with f together and everything with g together. It just like make it easier to solve, because when you have a lot of time, when you have a lot of things together and they're similar, you can look at the graph and see like, okay, if there's any trend or not. Now when you end up here, what is giving you, does this look familiar? You have two other derivatives by definition. So here is actually just f prime of 4 minus g prime of 4. And so f prime of 4 here is basically, as I said, the meaning of derivative at the point of a function is the slope of the tangent line. Now you look at the graph of f, and you see, you look at 4, right? So this is the tangent line, which is going to be a horizontal line. So the slope of f prime, so f prime at 4, so the slope of the tangent at 4 have the slope of is 0. So the slope is 0, so it's going to be 0 here. Now when you look at g at 4, when it crosses through that, is a straight line. So the tangent is going to be just the slope of this line itself. So now we have to figure out what is the slope over here of this straight line. Now it's rise over run when you try to find the slope, right? So you just, here is 4 unit and this one is 2 unit. So the slope here is just rise over run, which is 4 over 2, which is going to be -2. So this is a strange one, but I think it actually helps with everyone who understand the concept well. Now, before I go to, oh God, what is wrong with this board? Okay, give me a second, because it seems like the technology goes wrong a little bit. Keep this. Okay. So let me start it again. So before I go through section 2.2, is there any questions with what I just go over? These are kind of like a very basic problems that you guys should know for this session. Okay, if not, we're gonna go through the next section. So 2.2. So 2.2, making the concept of derivative a little bit more general, when it's actually categorized as a function instead of just evaluating it at a point. So we have derivative of f as a function is defined as f prime of x when you have is going to equal limit of h approaching 0, f of x plus h minus fx divided by h. Now this there are many ways that you can notate it. It can be written as f prime x or y prime if y is given as a function of x, or dy over dx. It's just a lot of them. Depending on what field that you're doing, because I remember if you proceed further to any field of like science or engineering, then you're gonna see this one when you're doing like, I think, Jaspit or something. It's like when you find dx and then dy. I don't know about all the field like algebra, statistic. I think you're gonna see things like this one, but for the rest, well, unless you get to like statistic 400 level, then they're gonna use it. But statistic doesn't usually deal with derivative. But yeah, that's like some of the notations that you guys should know in case that we need it. And then the meaning of f as a function, as I said, it's kind of like similar to the derivative at a point. So say if you have a function this way, so f prime is basically the slope of a point on that graph. So say the slope of the tangent. So say here you have, this is the tangent, and it's the f prime at value of f prime at that point is just gonna be the slope of the tangent, like here and there. So pretty similar to the previous session, not really new. The only thing that's new is the definition of differentiability. So a function f is differentiable at x equal a if these two conditions are satisfied. F is continuous at x equal a, or f prime a exists. So we need both of the conditions. So here you can clearly see the fact that if f is not continuous, you can immediately conclude that it's not differentiable at that point. So f is, yeah, the theorem is saying if f is differentiable at x equal a, then it is continuous. But if it's not continuous, you can immediately go back. However, if you have a continuous function, it doesn't go both ways. It's only one way. When you have differentiable, yes, you can conclude that it's continuous, but you cannot go the other way around. Yeah, and then we also have higher derivative. So instead of the first derivative as we just see, you can have the second derivative, the third derivative, and fourth. So by going through each of them, basically the step is just take derivative from of f prime. You're gonna have f double prime and then f triple prime, and then when you start to go to the fourth derivative, you're gonna denote it as f with f4 with 4 in the parentheses. So just like make it easier. You don't want to like read like a notation with like 5 different catastrophe on that. And so we're gonna go through the first example of this sessions. It's question 59, also of 2.2. I usually don't go through like the examples at the beginning of like that sessions, because those are usually very like basic, and I think Dr. Kasha kind of like go over them in her lectures. So when I want to do review sessions and kind of like make sure that you guys already understand it. So I'm just gonna go through like a little bit deeper in the exercise that we're gonna try. So given the function fx equal x absolute value of x, sketch the graph of the function. Find what value of x is f differentiable and find a formula for f prime. And I would say before we get started, I think this is a challenging one. So if you have any questions during my explanation, feel free to stop me at any time. So we're gonna get started. Before you want to sketch the graph of the function, we need to know like what actually how this thing look like, and maybe like the specific function, because usually the thing that's stick with the absolute value is that we have the rule of absolute value. So absolute value of x, as we learned before, it's gonna equal to itself if the value is positive. So the thing that you know about absolute value is that they're always positive. So it's gonna say if you have absolute value of 3, it's gonna equal to 3 because 3 is bigger than 0. But if you have absolute value of -3, it's gonna be 3, but it's actually the other way that you can write is negative of -3. It's gonna give you the saying that the absolute value of x is gonna equal negative x if x is smaller than 0. Just like here. When you have absolute of -3, it's the negative of itself because it's a negative number. Therefore, we have fx equal x, absolute value of x is actually equal x squared. So x multiply x if x is bigger than 0 and is equal negative x squared if x is smaller than 0. Now it makes life so much easier because now you can see that you have two different it's kind of like a piecewise functions where you can just graph each part of them individually. And so when you try to graph it, 0, x, and y. So when x is bigger than 0, it's going to be in the form of x squared. So it's this way. It's a parabola. And on the other hand, it's negative of x squared. It's going to be this way. So this is the graph of fx. At 0, when you plug in, it's 0 for both of them. Will give you 0. So that is the graph of the functions. Any questions so far? Anyone like confused with the absolute value? Because I know it can be confusing to some other people, but you're gonna see it a lot in this class, especially when you try to go through my examples later when we learn about like derivative, first, second derivative test and all of that, like maximum, minimum. Those are gonna be the thing that we will see. So if there's no questions, I'll continue with part B. For what value of x is f differentiable? So to find where it's differentiable, we will use the definition of derivative at a function to find on each interval. So say if you have x bigger than or equal to 0, the definition gives you limit of h approaching 0, f of x plus h minus f x divided by h. Now this one is equal limit h approaching 0, x plus h squared. When you're talking about this part is a positive, so we're going to use this function up here. Minus x squared divided by h. And if you expand the square, it's going to be x squared plus 2xh plus h squared minus x squared divided by h. And what we end up having is that we have 2xh plus h squared divided by h, or just 2x plus h. And when h approach 0, now you can just plug it in and what you end up having is 2x. Now, when we think about 2x, so what we have from B is when x is bigger than 0, bigger than or equal to 0, f prime of x is 2x. And 2x is a polynomial. So the thing that we all know about polynomial, and I think from the previous lectures as well, is that they're continuous everywhere, which means that f prime of x will have a value on with every x from negative infinity to positive infinity. So basically everywhere. Now if we try to do the same thing for the other one. So in this case, up here we already conclude that it's differentiable on 0 to infinity because x here is restricted. So even though you know that this function itself is defined everywhere, but your x here is confined by the definition that gives us this form of the function. Now we're going to try to do similar thing for the other side. So this only one prime. So limit x approaching h approaching 0, negative of x plus h squared minus, and then minus x squared. So over h. So if you expand the square again and try to solve for what we have, what you end up having is that you're going to have negative 2xh negative h squared. And we kind of like do the same thing. It's going to give us negative 2x. And then again, this one is defined and continuous everywhere. Therefore, we have f is differentiable on negative infinity to 0, because it's restricted domain that can give us this form of the function. So when you try to plug these things into like this form of the function, you have to see what domain are you looking at, because you clearly you can have two regions when it comes to absolute value. Therefore, from this one star and then 2 star, we have f is differentiable on negative infinity to positive infinity. So basically we're saying f has its derivative exists everywhere. Yeah. Now we have part C. Find a formula for f prime. We already kind of like did that. So we have f prime of x it has two forms. It's going to be equal to x if x is bigger than or equal to 0, and it's going to equal negative 2x if x is smaller than 0. So that's also my final answer for this questions. Anything that you don't understand? Do you have anything that you want to ask about? Am I going too fast, or is it a good pace for you? Okay, so we're gonna go through the next example. Please feel free to stop me if you don't understand, because I mean, without feedbacks, I wouldn't really know like where you guys are in the class. So example 5, match the graph of each function with derivative. Again, I always try to make, as like an engineering student, I try to make a lot of them related to like applications and especially things that's easy to visualize. So hope you guys will enjoy this one. So to find what graph match with the derivative, so here is the graph of the function f, and here is different graph of f prime. So how do you actually do that? Well, we actually gonna talk more about this in, I think, around the time of midterm 2, but that is when you get to super complicated cases already. So here we can just do the simple one, since we're trying to understand the meaning of derivative. So as I said, the meaning of derivative graphically is that it's the slope of a tangent of that function. So if you want to know which match with, it's easy if you just look at like the slope. So say, look at A as example. Here you have, the graph is going down and then go up and then go down. So here, say if you pick a point just randomly, like here, here, there, and then up that. So when you draw a tangent line, what does it give you? So the tangent line here is downward sloping, so it means the slope is negative. Up to here is a horizontal line, so it's 0. Now it's positive again, then it's 0, and then it's negative. So you have to find a graph that will be negative, going from negative to cross 0, cross the horizontal axis, and then it's go positive, and then it go to 0 again, and then negative. So when you look at these 4 graphs over here, okay, you have negative until some point on the left, so negative on some point. So this is positive, so this is not right. This is negative, this is positive, might be right. But it doesn't cross 0 at 2 points, it only crosses at once, and it's at 0. Here you can see like the slope is at 0 at 2 points. So you have to find a graph that cross the horizontal axis twice, which is going to be 2. So you have 2 is going to go with A. Is that clear to anyone? Like this is the negative part, and then it crosses 0, and then this part up here is positive, and then it crosses 0 again and has become negative. Is it clear to you, like how we choose this graph? Okay, so then we're gonna go through B, C, and D. So for B, here you can see the fact that the graph is a straight line, and then it goes down and straight. So when you have a straight line, what happened with the tangent? The tangent will have the same slope with the graph. So, and then when you have a straight line, the slope is constant. So among those three left, only this graph have the slope is constant when you see like these horizontal line. But what about these hollow point? So what happened is that when you have these sharp corner, so the sharp corner is kind of like a graphical demonstration that telling you there's no derivative at that point, because as you can see it's the limit when the slope approaching on the two side, and then here the slope is positive and here the slope is negative. Of course they're not going to be equal to one another. Based on the definition of derivative, is the limit of h approaching 0 fx plus h minus fx over. Okay, so question about that? Sure. Give me, yeah, it's in that one. What do you want to ask about, like what I'm saying, or at what point do we define it does have a derivative? Oh, okay. So as we say, at what point do we define we have a derivative? So as I said in earlier, when you want, so if it has a derivative there, it means that it's differentiable at that point. And the two conditions that we need is that f have to be continuous at that point, and the limit, like f prime a, like the two conditions here. These two conditions have to be satisfied. So first you need a continuous graph, which we were having when we have this kind of graph, but the second condition is not satisfied. That's why I'm saying it's not. So when you want to see if that at that point you have derivative or not, first you check for continuity. Is it continuous or not? If it's not, you can immediately conclude that okay, there's no derivative there. However, if it's continuous, you have to look graphically if there's any sharp corner like this, or yeah, and then or like this thing. So what happened with the graph of absolute value of x is that it have this thing here that gives us no derivative. And if you actually find the limit, so say the limit here is the definition of derivative. What it means graphically is the slope, right? When you look at here, you approach it on one side. The slope is a positive number because it's a positive slope. When you approach it on the other side, it's a negative slope. What can you conclude about the limit over there? You just learned last week. If you want a limit to exist at that point, you need both limit on both sides to equal to one another. Here, the limit on two sides are not equal. That's what happened with the sharp corner. Like here, this is positive, this is negative. That's why you don't have a limit. 175 degree. Oh, okay, you have it. Okay. Yeah, so yeah, that's better. Okay. Yeah, I mean it's a little bit new to someone, to some people, because it's kind of like it's really hard to think. Actually, like a lot of people don't relate calculus with graphical thing, but when it comes to graph, I feel like it's make it so much easier to like remember and understand. So I try to put it in, but if you are confused like that, feel free to stop me at any time. I would love to talk about these things. Yeah. So back to this problem. So when we have these sharp corner, it means that you don't have derivative. So when you look at the graph of derivative on the right, like these, when you have these hollow points, it means that there's no value exists at that point. And I think, and that is kind of like one of the way that you can determine it. Another way to check it is that the slope, as I said, when you have a straight line, the slope is constant. So here is a negative constant. So, oh, actually it's going up. So it's a positive constant. So this is above 0, so it's positive. And then this is going down, so this is a negative, and it's a constant as well. And then this is going back to positive again. And at these points, there's no value. So that's one of the way that you check. So the way that we're going to solve these problems is that you have to understand the meaning of derivative, both graphically and maybe like some special case of it. And I mean, most of them just come from a lot of practice. And I mean, don't worry, like when you do practice and you're like, oh, I have no idea how to solve this problem, feel free to like shoot me an email. I wouldn't be able to like talk in person, honestly, or like maybe I can schedule like a meeting with you guys, but yeah, one of the way is explained through email. I think a lot of times one of the ways that when I start writing questions to my professor, sometimes I don't even need to write, because as I write it, I figure out what's wrong with my thinking and how I can solve the problem. So yeah. So now we're going to C and D. So C, when you have, again, you're looking at the graph, you choose some random point and see what the train of the tangent, slope of tangent is going to lead you. So here you have a negative slope. It's slightly going down. And then you have a 0 here. And then it's going back. So then you have slightly negative, 0, and then positive. Now you now you look at this here. You have, there are only 2 left. Slightly negative. So as you can see here, before it reached this point in the middle, all of the slope are negative. And it's just go like slightly negative, more negative, and then go to 0 again. So if you look at here, then some part of it is positive, which is not the one. So our answer is going to be 1 is going to go with C, and then 3 is going to go with D. Now to check back with D, you can see like the special pointer give you horizontal tangent, which is going to give the slope at 0, which meaning your derivative graph have to cut the horizontal line 3 times, like 1, 2, 3. So you have cut 1, 2, 3. So that is the correct answer. So before I go to, I think it's 2.3, any questions with these problems? Okay, so if there's no questions, I'll go to 2.3. So 2.3 is basically help you to just like, okay, say if you're given a common functions like polynomial, like this one, or like things like x squared, x cubed, x7, all of that, you don't need to go through like the tedious thing of finding the limit every single time, but now you can actually apply it. But I mean, to derive these equations, basically they do the same thing. They use a limit thing, and they come up with this kind of like a generalization for you guys to apply. So it saves time, but then we should go through the definition function. Like we have to learn that before this to kind of like understand, okay, how the hell do they get these formula? So using some of the common formulas, so say if you have derivative of a constant, so C here is a constant, it's going to be 0. Derivative of x with respect to x, so this is the part where we say with respect to x, it's going to be 1. And then we have a general one for derivative of x to the n with respect to x is going to be n x to the n minus 1. Another one is you have a scalar multiple of a function, so a constant multiply a function, and you want to take derivative of that. You can just take that constant out and take derivative of a function if f is differentiable. So this one is only valid if f is differentiable. So if this thing is not differentiable, meaning it doesn't exist, I mean, there's no point multiplying a constant to a not existing value. And then we have sum and difference of a derivative is here. So when you have derivative of a sum or a difference, it's going to be equal to the sum or the difference of the two derivative complementary if both of them exist again. Now, we also have some other rules called product rule and quotient rule. So if you are asked to take derivative of product, it's gonna be in this form. You're gonna see that clearer if we actually jump to like doing examples, or I think you might have seen it in the lectures. And if you have quotient rule, just make sure the fact that the derivative in the denominator, no, not derivative, the function in the denominator is not 0. Both of them need to be differentiable, because you can see here f prime and g prime. They should exist so that this expression is valid. Now let's go do example. So example 6 is question 27 of section 2.3. So they give you this function and they ask you to find it. What's the derivative? So it looks a little bit frightening, but we can solve it. It's just one of the steps. I also want to show you guys how to rewrite the equation, because not just in 140, if you actually proceed to 141, a lot of time if you actually see these, I think the first midterm only, because I also do 141, is that a lot of time when you rewrite the function, it makes your life so much easier to take integration and all of that. So it's one of the technique that I want to show you as well. So rewrite this. 1 over y squared is just y to the negative 2. So basically, just like familiarize yourself with the concept of negative power. So we usually see x cubed, x fourth, but have you ever thought about x to the negative 3? It's just 1 over x cubed. That's like how we rewrite negative power in the reciprocal way. So here we have we can rewrite that, and then y plus 5y cubed. Now, the first thing when we look about this is that, okay, we have a difference here and then a sum there, but what connects them together, or the biggest expression, is basically you have a product. So when you look at this, you have product. So you're going to start with the product first before doing the sum and difference. So what we have here is we have to take derivative of the thing on the left, multiply y plus 5y cubed plus, because it's f prime g plus g f g prime, so y negative 2 minus 3 to negative 4, multiply the derivative of the one on the right. Now here we use the general formula, d over dx of x to the n is going to be n x n minus 1, and n just need to be different from negative. Yeah, it's just have some conditions going along with it. I don't quite remember, but yeah, that's the case. So here we have derivative of this is going to be negative 2, n is negative 2, y to the negative 3 minus 3 multiply negative 4, so it's going to be plus 12, and then y plus 5y cubed plus negative y to negative 2 minus 3 to the negative 4. Now here, y, your n here is equal to 1. So it's 1 plus 15 y squared. So what we end up having now is that just distribute them together. What we have is negative 2 y negative 2 plus 12 negative 4, 10 y to negative 3 with y cubed is just y to the 0, which is just 1, plus 60 y negative 2. Is it not easier to expand the two expression by multiplying? Yeah, I mean, you can do that. I mean, I'm just trying to like show the fact that you can use product rule and then chain rule. I mean, there are multiple ways to do this problem. That's actually a good idea. Yeah, I just try to like apply the product rule and then the kind of like the general formula. But yeah, sure. I mean, it's the same. Yeah, I mean, it's the same. How the answer are expressed. Okay. Um, what do you mean by that? Like when I get the final answer, how should I write it? Like it as a, it's only one or two different ways to give an answer. Okay. Um, I don't know how website take those values. I think either way, say if you put in the values and like it doesn't give you the marks, you can always send an email to Dr. Casino because it's mathematically correct. It's just like sometimes we have like more than maybe like three expressions to give the same answer. So yeah, sometimes you just have to like check your quiz after you take it. Um, as long as you can prove to Dr. Casher that it's the same, I think you get the credit because that's mathematically correct and that's all the thing that actually matters. So yeah, so we'll put it this way. Yeah, I'm just trying to figure out where am I. Okay, yeah, we have that. Okay, sure. Now we just continue to do the multiplication over here. Yeah, don't worry, don't worry. Yeah, it actually helps. I feel so much better than when people actually ask me questions. The entire last semester is just me doing the sessions alone because the timing doesn't actually work. In the spring semester, I'm like halfway in Australia and halfway in Vietnam, so it's a little bit odd to actually figure out what is going on. Trying to like I'm dealing with like three different time zones right now: US, Vietnam, and Australia. So it's a little bit stressful, but it's good. Like I feel interactive. So now we're just gonna simplify it. Um, negative 2, 60, 61. So it's 59 minus 45. So it's gonna be 14 y to negative 2. Just want to check back with, yeah, number wise I'm not really great with it. Negative 4 plus 5, 5 or 15, 5. Wait, hang on, it's a 15. Didn't make a mistake anywhere. Oh, negative 10, we forgot. Right, that's 4, 5, okay. And then the last part. So now we can express it at 14 over y squared plus 9 over y fourth plus 5. Okay, so that is two ways that you can express the questions. Oh no, express the answer. I think both of them will be valid, unless it's like specifying specifically. So if you do the questions, make sure that you take care of things like saying, if you have like a small parenthesis for instructions saying like, okay, should express everything in like fraction or stuff. But sometimes website is a bit weird. Um, Basically, the answer that you put in is accepted or not depending on the instructor if they put on all the form of the answers. But there are times that you have more than like 5 ways to express the answer, so it's really hard to actually like construct how to grade those questions. Like, I mean, instructor doesn't really have time to like put on kind of like form of answers there. But yeah, but whenever you can make sure that okay, you check it back and you know that it gives the same thing, yeah, feel free to like ask for the grade for it. So that is example 6. We're gonna go example 7. It's question 107 in the book. So this is one of my favorite. The first time when I do my 140, I look at this one. I have no idea how to do it, but I feel like it's a very helpful one because it relates to definition of um. So when you look at here, it's the limit x approaching 1, x to the 1000 minus 1 over x minus 1. So does anyone have any idea how to do this before I solve it? I just want to make sure like we're on the same page. I'll give you like 30 seconds, think about it. Okay, so does anyone come up with how to solve these questions? Okay, I'm gonna solve it. When we have limit, so when we look at this limit, the first thing that comes into my mind, so when I plug in x equal 1, I'm going to have 1 minus 1 over 1 minus 1, which is not giving me anything because it's 0 over 0. And I mean, I haven't learned anything about how to solve 0 over 0. So what I try to do is that see, okay, is there any other different way except for plugging it in? And since we're doing kind of like derivative, and this limit kind of reminds me of 2.1 is derivative as a point. So we have x to 1,000. Just to make sure, I rewrite it at x minus 1. So this one is because I have, when you have like the definition of limit, like approaching a, fx minus fa over x minus a. It kind of reminds me of that. But fa, what value, what is the function here? The function here is x to 1,000. So instead of 1, I can write it at 1 to 1,000. And it makes perfect sense to match these two together with a equal 1. So therefore, I can conclude that it's f prime of 1 with fx equal to x to 1,000. Now, to do this, we just learned like actually x to the n, how to take derivative of that. So we have f prime of x is 1,000, x to the 999. And so we have f prime of 1 is just plugging it in. So which is going to be 1,000. So that is the value for this limit. Does it make sense to you? It's actually a very interesting one. It's like my favorite. Again, if I say it, talk too fast, just stop me at any time. If there's no questions, I'm gonna proceed to the last section today, which is 2.4. So 2.4 is derivative of trigonometric functions. Not only that, we also get to introduce to some of the special limit that I think we're gonna use not just here, but I remember in 141 you definitely see it. So we have the special limit, and it's actually I think I mean I don't want to like go through how to prove it, but it actually resolve a lot of problems that when you say you have limit of x approaching 0, sine x over x. Again, the first approach that to do with limit all the time is plug in, and what you have is going to be 0 over 0, and it's not giving us anything. So kind of like mathematicians somehow determine that it's gonna, this limit, meaning the rate that both of them approach 0 is gonna be the same, which is gonna give 1. And then we have some other similar limit that get derived some other way. Another way to remember tangent x over x with limit of x approaching 0 is that you have sine x over x of 1 over cosine x. So basically rewrite tangent as sine x over cosine x. And this one, from here, you have is equal to 1. And then this one, as x approaching 0, 1 over cosine 0 is just going to be 1 because cosine 0 is 1. So it's make remembering easier when you actually understand how to like, okay, there's more than one way that you can rewrite it. And then we have derivative of trigonometric functions, sine, cosine, tangent, cotangent, secant, cosecant. In this class so far, the most common that I see is these 4. I don't think you guys actually do anything with these 2 until you get to 141, when we actually have integration, where you need to know like a lot more functions. But yeah, like most of the thing that you're gonna see is just sine and cosine, so it shouldn't go too crazy. Sometimes we have tangent. I've never actually seen cotangent, but if you actually look at my practice problems, you're gonna see a lot of cotangent because I try to make things harder for people. I know. But yeah, that's 2.4. Now we're gonna go to examples. So I remember I only have 2 examples for this, and then we have practice problems. So good. Okay, example 8. It's question 26. So it's asking us to find an equation of a tangent line to this curve, which is y equal 3x plus 6 cosine x at pi over 3, pi plus 3. So yeah, we can use the formula that we have earlier. So when we're trying to find the equation of a tangent line, and this is one of the things you're gonna see me using a lot in this class. So I will always start up every question asking you about tangent line by asking you, what is the general formula for the tangent line? So this formula should actually go in depth into your mind. It's going to be f prime at x0, which x0 is the point that we're trying to find the tangent at, x minus x0 plus y0. So x0 and y0 is the coordinates of that point, which is this like here. So this is the general formula. So to find a tangent line, first we need the slope. Second, we need the coordinates. Here we're given the coordinates already, so we just need to find the slope of the tangent. And as I said, the meaning of derivative is the slope of a tangent at that point. So basically we have to find derivative of this function and then plug pi over 3 in. So you have y prime is equal. This is a polynomial. So derivative of 3x is just going to be 3 because derivative of x with respect to x is 1. So 3. The other one is x 6 cosine x. Derivative of when you have a constant multiply function, take 6 out, and the derivative of cosine x is negative sine x. So what we have is 3 minus 6 sine x. Now, we plug in pi over 3. So y prime at pi over 3 is going to equal 3 minus 6 sine of pi over 3. And so sine of pi over 3, if you look at the end of the book, there's some of the special angles. You don't need to remember it, but as long as you do a lot of practice, I think it'll just like naturally come into your mind. Sine of pi over 3, as I look at my unit circular, is going to be square root of 3 over 2. So it's going to be 3 minus 6 square root of 3 over 2, or 3 minus 3 square root of 3. Now we just need to plug everything in to find tangent. Tangent line. Y equal 3. This is the slope. X minus pi over 3 plus pi plus 3. Or you can try to like further simplify it. I try, but it doesn't really simplify that much. So I'll just keep it that way. Question 26. Okay, so that's my final answer, the tangent line. So things that you remember here, this special formula, I'll ask you several times this semester. I promise. But doing that, that's a very important equations in calculus. Now, if we try to graph it out, this is how it actually looks. So this is the point that we're trying to find a tangent, and this is the tangent line with the graph. And here I also want to introduce you to one of the very helpful graphing software that I always use to, and I think it helps even not just in 140, 141, but also in 230 and not 251, but 230, 231, 232. So it's because it's kind of like give me the general idea of like how my graph 2D or 3D look like. It doesn't have 3D graphing, but if you want to see like how like a cross-sectional area of say like a solid look like, this is how one of the way that you figure it out if you have the functions already. So now we're going to go to the last example. Example 9, find the points on this curve at which the tangent is horizontal. Now, as I said, I'll ask you what's the general formula of a tangent line. So the general formula of a tangent line, as I just wrote down in the previous example, is this one. When you have a tangent is horizontal, what it means is that the slope is equal to 0. Say this is the horizontal tangent. So the slope is 0. So basically it's asking you to find x at which f prime of x is equal to 0. So that's what basically it helps to find. And the way that we interpret the questions to mathematical symbol is very important, especially when you come to midterm 1, midterm 2, or everything in life. Everything is in a word problem. You should have that ability to interpret everything into what you already learned and try to solve it. Obviously, in say like going to a bank or industry where they give you like a project and they're like, okay, find me this quantity. They never tell you like, okay, find me whatever, like what is rate of growth or like f prime, or like they will never tell you that. They will ask you, okay, how fast does it growth? How do I determine what is the cost of this last unit? That's the marginal cost. But no one actually, if you don't have this ability to interpret word problems into mathematical symbols, that's gonna make your life a little bit miserable, honestly. So here, I was just want to say, come back to the questions. We just find what is f prime of x. Here, we use the quotient rule. You have 2 plus sine x square. You have, it's gonna, and let me put it back here, f over g. Take it. It's gonna be g squared, f prime g minus f g prime. So what we have so far, so f is cosine x, so it's gonna be negative sine x. Multiply 2 plus sine x, negative cosine x. G prime is just cosine, because derivative of 2 is 0 and derivative of sine is cosine. So what we end up having is negative sine square x, negative cosine square x, divided by 2 plus sine x squared. So another thing I want to show you is you guys might be familiar with this one in maybe like high school or like whatever math that you took before. So sine squared plus cosine squared is equal to 1. If you haven't seen this thing before, this is kind of like one of the very old mathematical expression in trigonometry. So it's a very good thing to know. Why am I putting it up? Because here when you take the negative out, you have negative sine x. Take negative out, you have sine square x plus cosine square x, which is just going to be 1. And it's make things so much easier. So what we end up having is negative 2 sine x, negative 1 over this. Now we try to find what value of x is going to give our derivative equal to 0. Now we have a fraction here, and for a fraction, when you want it to be equal to 0, the denominator have to be different from 0, and the numerator have to be 0. Now denominator have to be different from 0, so that the fraction is defined, and then it have the value of 0. 2 plus sine x squared is always bigger than 0 because sine x is squeezed between negative 1 and 1. So when you add 2 in, what we have is 3 and then 1. So it's always positive, and when you square, it's always going to be a positive number. So what we need to find is that f prime of x is equal to 0 when you have negative 2 sine x, negative 1 equal to 0. Or you have sine x equal to negative 1 over 2, or it will give you x equal negative 1 over 2 sine x is going to give you negative pi over 6 or 7 pi over 6. So yeah, that's the end of this session today. Is there any questions with this problem? If we don't, so I will put these are some of the practice problems that I put on, and you guys can try it out after you already done all the suggested problem. All for your sake of practice. I know a lot of us are like adult learners. Oh, I mean, except for me, maybe, because yeah. But Yeah, sure. My email. So a few final notes before we end the session is that a lot of us I know are very busy with work, and I know you guys have to work extra, maybe like during weekend or at night to keep up with these classwork. So I am one of the resources that Penn State is providing to you. So feel free to email me anytime you have questions or you want to schedule a meeting. We can see like face to face with the same link, just at a different time. And with my a little bit messed up schedule, we just have to figure something out. But as long as we communicate, everything's gonna be good. This is my email. Feel free to email me. I mean, as long as it doesn't have anything to do with grading or like, okay, I submit my homework late or like I need someone help to schedule an exam. Those things I cannot help, but anything related to calculus, I will be more than happy to answer. Um, and then, yeah, every single time you join these sessions, please put in that ABC1234 or like the PSU email, just like as like a yeah. Just give me a second to finish this. So like we have the yeah, just put it in the chat room so that I can keep up with the attendance and I don't have to like repeat it so many times and bore other people out. So yeah, that's all I have for today. If you want to leave, feel free to do that. Taryn, can you get back to me with the questions? Yeah, I can answer it now. Do you want to put it in the chat room? Or I can just like unmute you to in the book problem 37. Okay.
Yeah, I can talk with the microphone. So problem 37, 2.3
Okay.
is
I think you need to like tell me what that is because obviously I'm in
yeah,
Australia and I don't have the book. So
yeah. Oh, okay. So it's cube root t over t minus 3
is the cubic
um,
root also include t minus 3 or not?
outside.
Outside, so t minus 3, like the one I have on the screen right now.
Yeah.
Yeah, and then what is the questions?
So like, it's just kind of like more about what I asked before. Like basically, just at what point like you're supposed to stop, because like looking at the I don't know if I can I actually show you my screen? Yeah. I don't know if you
Give
can.
me a second. I think you can do that, but I need to stop my sharing screen first. And I don't know how to stop sharing this screen. Okay, give me a second. Okay, stop share. I got it. So yeah, can you?
Okay, so I have two. I don't know if you can you read those?
Yeah, I can.
Okay, so those are the answers, and you can see the one on the right is the more simplified version.
Yeah.
Um, but the first box that I like squared off on the left, like
Mm-hmm.
why why can't you just stop there? For
I mean,
example.
honestly, if it was me, I would stop there.
Okay, because I spent way too much time fucking around with that.
Yeah.
Because
Um.
like,
Yeah. I mean, one of the problem with the book solutions, honestly, since I started doing calculus, I never actually look at it because sometimes it's just being really
it
weird.
drives me was literally driving me crazy. And I mean, I just started doing math recently. I mean, I basically like taught myself um like on Khan Academy and stuff for a long time. And so like I am still like literally before I started this calculus class, I was just learning about like the powers and stuff. Like I didn't know how to do that stuff. So it's like I'm going through this stuff and I understand the concepts, but I definitely like have issues with the solving some of this stuff, especially like those specific types of problems. It took me a long time to figure out, but I ended up figuring them out. But like it seemed to me like there was just a point where I didn't know where to
When to
stop.
stop? Yeah.
And like, yeah, it didn't seem like there was any sort of difference. I mean, especially with powers and stuff like that, you can put it on whatever side of the fraction that you want, and
Yeah. Yeah, that's
yeah,
completely true. Honestly, yeah, I mean, you just started. I need 12 years, no, actually 18 years doing math in my entire life before I go to college to get that intuition. So there's no pressure on you. So don't press yourself to like try to figure out where to stop. Um, I feel like a lot of even like the current student at Penn State also ask me the same question. So it's a general problem, but I think you're in the right directions of what you're doing because the intuition will, it comes a lot on practice, and look at what you're doing. I feel like you're getting there. Like, I mean, you don't need to go to the final answer as in the book because that doesn't mean that, okay, you understand the problem. What I've seen so far is that you actually understand the problem. You don't need to follow everything in the book, honestly.
Right.
Yeah.
Yeah. As long as I get as long as I get. Well, I mean, that's kind of what I was asking about, is because I just don't want to like be taking the test and then like. I mean, I just.
Yeah, the test is not typing out the answer, it's multiple choice, so nothing to worry about.
Okay. Cool.
Yeah, like as long as you look at the form of the answer in the book and you can, no, not like in the book, but like in the actual exam, because it's like multiple choice. So most of the time you can manipulate them and see like if you can do some like algebra to match them with the final answer, it as in the exam. So that's, you're gonna be in a good shape.
Yeah. And
Yeah.
so we can obviously use like paper and stuff in the exams.
Yeah. You can feel free to do anything except for accessing the internet and ask other people.
But we can't use notes.
I don't think so.
Yeah. Okay.
You have, I think what happened with Examity is that they let you schedule a time and they have someone watching you doing the exam at that time. I think so, but I have no idea because that, I think that's like the only reason that they can ask you to schedule a time, because if there's no one watching you, there's no point of scheduling it. But I think you have access to calculators, which is not supposed to be, for real, for in reality. But I mean, it just helped with doing quizzes and homework. But I would say in actual exam, don't try to do it if they are watching
Well,
you. Yeah.
are you saying? Yeah. No, I don't think we can. We can't use we can't use calculators in the actual exam. I don't think.
Yeah, I don't think we
But
can do that either in paper or in person. It's not happening. Yeah.
yeah.
But I mean, the
Okay.
calculations in the exam, because they know the fact that you don't have calculator, everything is super simplified. It's all about doing actual calculus. So, no, like it's not an algebra class. They're not asking you crazy calculations.
Right. Um. Let me see. Let me think. Do you have time, or
Yeah,
you gotta go?
sure.
Let
That's
me
fine. That's fine.
let me think real quick about if I had any other like super weird things that I
Yeah,
ran
then
into.
just give me a second. I just need to like maybe unrecord, stop the recording.